Have you ever been on a flight, maybe 30,000 feet in the air, looked out at the wing, kind of flexing in the turbulence, and just thought to yourself, how in the world is this giant metal tube staying together? It's an absolutely incredible feat of engineering. So today, let's break down exactly how these marvels are built, piece by piece. Okay, so take a look at these two. On one side, you've got a simple, graceful hot air balloon. On the other, the incredibly complex space shuttle. They seem like they're from different universes, right? But believe it or not, they share one really important thing in common.
And that is, they're both technically aircraft. But that seems like a ridiculously broad category, doesn't it? I mean, come on. So what does that word actually mean?
Well, turns out the official definition is surprisingly simple. An aircraft is just any device that can lift off the ground and move through the air. That's it. It's a category so huge it covers everything from a toy kite to a rocket blasting into orbit. So this massive family of flying things basically splits into three main groups. You've got your aerostats. These are the floaters, the things that are lighter than air, like hot air balloons. Then there are the aerodynamics, which are heavier than air and have to work to create lifts, like airplanes and helicopters. And finally, you've got aerospace vehicles, like the shuttle, that use this wild mix of aerodynamics and just pure raw power. Now, that is a lot of sky to cover. So for our deep dive today, we're going to zoom in on the one we're all most familiar with, the absolute workhorse of the sky, the airplane.
All right, let's get right into it. We're going to start with the basics, the anatomy of an airplane, because, it's a whole lot more than just a pair of wings.
So when you look at a plane, you can see the main components pretty clearly. You've got the wings, of course. They generate the lift. You've got the empennage, that's the fancy word for the tail assembly, which gives it stability and control. But the piece that holds it all together, the very heart of the structure, is that main body, the fuselage.
Now, it might look like it's just a tube for us and our luggage, but the fuselage's job is so much more critical than that. So what does it really do?
Well, think of the fuselage as the backbone of the entire aircraft. Yeah, it houses the cockpit, the cabin, and all the cargo. But way more importantly, it's the central pillar that the wings and the tail are literally bolted onto. It also shields all the vital control systems running through the plane, and sometimes it even holds the fuel. Everything is built around it. Okay, so if the fuselage is the backbone, that presents a massive engineering challenge, right? How do you build one that's both incredibly strong and impossibly light? Well, this is where the story of how planes are built gets really, really cool. Early on, planes used something called a framework construction, often a Warren Truss design, like you see here. Just think of it as a rigid skeleton made of steel tubes. A lot like a bridge. It's definitely strong, but it's also really heavy, and trying to wrap an aerodynamic skin around that complex skeleton is just not very efficient. So engineers tried the complete opposite approach, monocoque construction. The name means single shell, and the best way to think about it is an egg. The outer skin carries all the stress. It's super lightweight and smooth, which is great, but it has one major, you guessed it, egg-like weakness. One little dent, one little crack can compromise the entire structure. Not ideal. Clearly, the pure skeleton was too heavy, and the pure eggshell was too fragile. The perfect solution had to be somewhere in the middle. So engineers brilliantly combined the best of both worlds. And that brings us to this, semi-monocoque construction. This is the gold standard for pretty much every modern aircraft. The skin still carries most of the load, but now it's reinforced by an internal skeleton. You have these circular frames that give it its shape, and then you have longerons and smaller stringers running the length of the plane. This combination gives you the absolute best strength-to-weight ratio possible. And trust me, that structure needs to be tough, because a plane in flight is under constant attack from all these incredible forces. It's being pulled apart by tension, squeezed by compression, and twisted by torsion all at the same time. The semi-monocoque design is just genius because it distributes all those stresses across both the skin and that internal skeleton. But a brilliant design is only as good as the stuff it's made of, right? That brings us to our next section, the amazing recipe of metals and composites that make modern flight even possible. For decades, the king of the castle was aluminum alloy. It's got that amazing strength-to-weight ratio, which makes it perfect for the main skin of the fuselage and wings. But in super hot areas, like around the engines, you need something tougher, and that's where titanium comes in. It handles heat and corrosion like a champ, And for parts that are under constant repetitive stress, like the tracks the wing flaps move on, you need the brute strength of steel. But here's the thing. Metals, they're really only part of the story now. The true revolution in modern aircraft, the real game changer, has been composite materials. Think of these two like a superhero duo. You've got Kevlar, which is the tough defender. It's got incredible impact resistance. I mean, it's what they make bulletproof vests out of. Then you've got carbon fiber. It's the strong, lightweight athlete, providing the insane stiffness and strength you need for major parts like the wings and tail. And this is how they often use them. And it's just brilliant. You take two super thin, super strong sheets like carbon fiber, and you bond them to a super lightweight honeycomb core in the middle. What you get is a panel that's unbelievably strong and rigid, yet weighs almost nothing. It's pure engineering magic. So let's put it all together. This image is fantastic because it shows you exactly how a modern airliner is this complex patchwork of different materials, each one picked for a very specific job. The green you see is carbon fiber, making up the wings and tail for that critical stiffness. The purple is Aramid, or Kevlar, used in places that need to be extra tough. It's really a symphony of material science. What this all boils down to is that nothing, and I mean nothing on a modern airplane, is there by accident. Every single component, from the tiniest rivet to the biggest wing panel, represents this perfect, deliberate balance in that constant engineering battle between strength, weight, and cost. All of this relentless innovation has gotten us to where we are today. And it just makes you wonder, right? What comes next? Where do we go from here? What could the future of flying possibly look like? Well, this could be one glimpse of that future. It's a concept called the double bubble fuselage, which could offer just massive fuel savings. From those first clunky truss frames to these futuristic composite designs, the story of the airplane has always been about pushing the boundaries. And it's a powerful reminder that this evolution, it's far from over. The next generation of flight is already taking shape on drawing boards as we speak.